Welcome to another video by Meston Educational Services. In this particular video, we are going to look at limits and continuity. We are going to look at limits and continuity. So before we can even start this class, there would be certain questions that we need to answer. When is a function said to be continuous? Or rather, we could ask the same question differently. What makes a function discontinuous? So what we may have to do is to determine the points of discontinuity and also be able to identify what is the nature of discontinuity. Then we will be looking at what are limits and how do we determine limits. And then we'll be introducing ourselves to the concept of the left side limit and the right side limit, which is also referred to as the lower limit from the left side and the upper limit from the right side. So let's understand this initially. So I've got a function sine x over x, and you can see the graph is the red graph. Now the domain for this function is it is defined everywhere except when x is 0, because if you look at the function, if the denominator for me becomes 0, that part there, then the function becomes undefined. So the function value at 0 is undefined. So the function is undefined at 0. But however, if I look at approaching the point 0, I can approach it from the left hand side, that's this side, or I can approach 0 from the right hand side. So when I'm approaching 0, it's actually trying to get to a value of 1. Now that point there is 1. So it's trying to get to a value of 1, but we know it does not get to 1. So this is what limit means. It's trying to get to a certain value from the left hand side and the right hand side. Now it is very likely it will actually get to that value, but in this particular case it does not get to that value because the function is not defined when x is 0. But the way we will read it, when x is approaching 0 from the left hand side, the function value is approaching 1. So we say that the limit is 1 at x equals 0. Likewise, if we are approaching the point 0 from the right hand side, we are still approaching the value of 1. So we say that the limit from the right hand side is 1. So once again, when we say the limit is 1, it's basically suggesting it is trying to get to that value. Now it is very likely it will get to that value, or that value actually does not exist. So this is what we understand by limits. It's approaching a certain value from the left or from the right when x is given a particular value. So let's just go and observe this on my calculator screen. So I'll just pause and go to my calculator screen quickly. So now if you look at my calculator screen, and I'm going to start actually moving this point, and I'll just drag this point and grab it from here. Now if you observe, when it gets to 0, it's giving the values over here. It gets to that point and actually it says that's undefined there, and it keeps going. So I'll just pause this and I'll try and put that value as 0, and let's see what happens. When I put that as 0, it comes up with this warning, cannot move the point to the requested location, because that point actually does not exist on the graph. It's undefined. However, if I try to move it to any other point, let's say if I move it to -1, it will go. If I move it to point 0009, and yes, and you can see it's trying to get to the value of 1. Now that's from the left hand side that we are approaching 0. What if I made that as 0.001, and now we are approaching from the right hand side, and let's go and just give it some more decimal places, and you'll see it's trying to get to that value. So whether from the left or from the right, it is trying to approach that value of 1. So when x approaches 0, it says the value is 1. Now I can approach it from the right hand side. If I want to approach from the right hand side, I need to put a plus, and you'll see it approaches 0. If I want to approach from the left hand side, negative, and you can see it still approaches 1. So from both the sides, when I say x is approaching 0, the limit is becoming 1. Now to understand the ideas of discontinuity, let's look at this particular expression. So I've got x minus 5 times x minus 2 in the numerator, which are the two factors in the numerator, and in the denominator I've got x minus 2. Now x minus 2 and x minus 2 can cancel out, and I'll get x minus 5 when it is simplified. However, when I click enter on my calculator, it comes up with this warning sign over here. So it says the domain of the result might be larger than the domain of the input. So in this particular case, it is saying if I put x equal to 2, the function is not defined. So it's giving me a warning, and you can actually see I've done that in the next step. I've gone and substituted x as 2 and it comes up as undefined. So if I said this and this mathematically are equal, yes, they are true, except for the fact that this one is not defined at x minus 2. So both will give me a straight line, but this straight line here will actually have a point of discontinuity, which I'll look at in the graphing screen. So here it says, if I put this expression equal to this, it says true, but again it displays a warning. And the warning is coming because here it says the domain of this section here is the function is defined everywhere except when x is 2. And with the straight line, if I didn't write that expression in that form, but if I just put x minus 5, I know that the domain is all real numbers. So that actually tells me if I was to graph this one here, it's going to be a straight line, but there will be a hole that will exist at 2. So a hole is actually creating a point of discontinuity. So the hole over here implies that point actually does not exist on the graph. Now the calculator screen will not show that very clearly, but let's just look at it. So let's go and change it to what we had. It's x, or we'll look at this one, doesn't matter. So x minus 1 and x minus 1 will cancel out. So what I have, this straight line is actually the graph for x minus 3. So you can clearly see the function value at 3 is defined. I can put any other value and it will be defined. So if I go and put 2, it's defined because it's giving me a value. But what about when x is 1? It says undefined. But let's look at the limits. So if I was trying to approach this point of 1 from the left hand side or from the right hand side, so if I approach it from the left hand side, you can see I've got the negative there. It says that the value is -2. So it's trying to get to the value of -2 when x is 1. And likewise, when I'm approaching the point 1 from the right hand side, it is still getting to the value of -2. So it's trying to get to the value of -2, but actually -2 as a y value does not exist on that graph. So this is what limits imply. So it's trying, if I was determining the limit of this function when x approaches 1 from either side, it is trying to get to the value of 2. Although 2 in this particular case is not defined, because we have just seen over here the function value at 1 is undefined. Okay, so that clarifies it, and this point is referred to as a hole. So let's go and actually put any point there. If I put 3, it will go there. If I put 1, it will go there. Sorry, it won't go there because it's undefined. So I'll just demonstrate something here. If I was to trace this graph, not plot the function, and if I start, so let's just do 1, and you can see it's moving there. And when it gets to that particular point for so it missed it because the step size was different. But if I just stop that again, so if I try to put that at 1, so it won't let me go. So before we can go any further, we just want to define a few very common limits. So the first limit is sine of x divided by x, where x is the angle. So if it is 0 degrees, what would happen? The denominator becomes 0, and that would be undefined. However, we do realize that when x approaches 0, we have already looked at the graph. This is trying to approach a value of 1. Either from the left or from the right, it does not matter. It's trying to get to that value of 1. So if we were to determine the value for this particular limit, which is sine of 9x divided by x, so the trick is to multiply the numerator and the denominator by 9 over 9, and then I can take that 9 outside as a constant, and I'll show you that comes in the rules for determining the limits. So if I take the 9 outside, now sine 9x over 9x would be 1, so that's going to be 9 times 1, which is 9. So as a general rule, if I'm finding the limit of sine of kx over x, all I need to do is to multiply both the numerator and the denominator by k over k, and then I can take this numerator k outside, so I'm left with limit of sine kx by kx when x approaches 0, and that would become 1, so it's k times 1, which gives me k. So these are the rules for finding the limits. So if I'm finding the limit of two functions together, I could actually find the limit by separating them. So x is approaching a, find for fx, and then do the same for gx, and then you can combine the limits. So that would give me the answer. However, obviously it is much easier doing it together in this form here. Same over here. This was the rule I was referring to previously. If I multiply a limit by a constant, or we give a coefficient, we can always take that outside. So I've taken that outside over here, and that's what we have done. So that would be this. Of course, k cannot be 0, because if k becomes 0, everything will become 0. So like addition, with the product of two functions as well, I can determine the limits individually and then multiply the limits to give me the limit of the combined function. But obviously this is always going to be an easier method to follow. And same with the quotient rule. So fx divided by gx, now we need to remember that cannot be 0. If that becomes 0, it becomes undefined. So in all these cases, x is approaching any numeric value which could be a. So we could find the individual limits and then divide them, or we can find the limit together. So once again, that cannot be 0 there. So this one here probably is one of the most important screens, because this is telling us what are the conditions for continuity. So these are the three conditions that we have to check. And for a function to be continuous, all three conditions have to be met. Even if one of the conditions is not met, then we say that there is a point of discontinuity at that given point. So over here, the point is A. So the first thing is we go and substitute a in the function, and it should give us a numeric value. So we are saying the function should be defined at that. So that's the first condition. The second condition is the limit at that point and the function value at the point should be equal. And at times it could be equal, but the third condition may fail, which is saying that the lower limit, that's when we approach the limit from the left, and the upper limit, that means approaching from the right, should also be equal. At times they may not be equal, especially if there is an asymptote or if there is a jump. So what could happen, the last condition is not met, but the second condition could still be met, and of course the first condition may also be met. So it is important that we check for all three conditions, but in saying so, if one of the conditions fails, we don't have to go and check the other two. And it's not necessary that we have to follow a particular order, but the first thing obviously is always to check if the function is defined at that point, because only then I'll go to check the limits. If the function is not defined, it's straight away a point of discontinuity. So next we need to examine what are some of the possible reasons for discontinuity. So the first reason is existence of a hole, which we have already talked about briefly. So if I look at this function, x minus 3 and x minus 1 in the numerator divided by x minus 1 in the denominator, this simplifies because x minus 1 and x minus 1 cancels. It gives me that the function is x minus 3, but at the same time the domain is x can take all real values except 1, because at 1 the denominator becomes 0 and the function does become undefined. So the function is undefined, and in this case, if I can look at it, the lower limit and the upper limit are same. So when I substitute that, and I'll show you on the calculator screen. So if the lower limit and the upper limit are the same, that means when I approach the point x equals 1 from the left and I approach it from the right, it is trying to approach a value of -2. So it may not get to -2, but it's trying to approach the value of -2 from both the sides. So the limit from the left hand side and from the right hand side is equal, but the function is still not defined at x equals 1, and it failed the first test. So what happens in this case, there is a point of discontinuity at x equals 1. So I didn't have to check this, but the reason I'm talking about that is because the two limits may be equal and the limit may be defined, but the function value is not defined. So that's what would be on my graphing screen. So if I show you, I'm trying to move my actually x value to 1, and it will not allow me to do that. I'm going to demonstrate that on my calculator screen now. So I'll just bring up my calculator. So when I'll click start animation, I want you to observe what happens to this value. So at the moment, my dot is sitting at 0.4, that's my point, and the y value is negative 2.6. So when I start the animation, I want you to look when it actually becomes 1. So it will go 0.4, 0.6. I'm moving in steps of 0.2, 0.8, and then 1. And I want you to observe what happens. So that's 0.6, and at 1 it actually came up with undefined. So you can see the results over here. The function value at 2 is negative 1. I can go and put any other value there. I can put 6 and it will say it's defined. But if I try to put there the value of 1, it says undefined, which is expected. So let's go and put it back to 2. And now if I try to move that point to 1, you can see it comes up with this warning, cannot move the point to the requested location. I can move it to any other point. I can move it as close to 1. If I put 0.9, it goes there. Or I could put 1.111 and it goes there, or 1.01. It goes to every point except it does not go to 1 at all, because that point does not exist on the graph. So that's a hole over there. So this is what we just saw. So let's look at what could be the second reason for discontinuity. The first reason was existence of a hole. The second over here is a graph we are familiar with, and this is a hyperbola, rectangular hyperbola. So the function is 5 over x plus 2. And we clearly know that there is a vertical asymptote at x equals negative 2. And we can see that. So the function is defined everywhere except when x is negative 2. Now I don't need to do the other tests for continuity because it has already failed the continuity test. But I'm just demonstrating something. If I approach this point negative 2 from the left hand side, which I'm doing, the function value actually gets to negative infinity. And interestingly, if I approach it from the right hand side, if I'm approaching negative 2 from the right hand side, it gets to infinity. So all of a sudden from negative infinity to positive infinity. So the limit is confused. So if I try to find the limit at negative 2, it will come up as undefined because the limit has two values from the left and the right. It has two different values. So the only time the limit will be defined at a given point is when the limit from the left hand side and the right hand side have the same value. So in this case, because they have two different values, the limit is undefined. So it has failed all three tests. So the first test was the function is not defined at negative 2. The second is the limit does not exist. So it's failed the test. And the third is the lower limit and the upper limit are not equal. So this particular case has failed all three tests. So if I was to look at the graph of it, that's the graph over there, and I can clearly see there is a vertical asymptote. And from the left, the graph, if I approach negative 2, it is approaching negative infinity. And likewise from the right, if I try to approach negative 2, it is approaching positive infinity. So the limit from the left hand side and the limit from the right hand side are approaching two different values. So there is a point of discontinuity. So just putting it on my calculator screen here. So when I put the function value as negative 2, it's undefined. The limit at negative 2 is undefined. The limit at negative 2 from the left hand side is approaching negative infinity, and likewise the limit from the right hand side when it's approaching negative 2 is approaching positive infinity. So that's the second reason for discontinuity. So when I'm back on my calculator screen, so that obviously is not defined. So when I put m as the function value was defined as m, sorry, the function name is m, that's undefined. The limit is undefined. The lower limit is negative infinity and the upper limit is positive. Now let's look at the third reason for discontinuity, and this happens when we actually talk of piecewise functions. So where there are two or more functions that are put together and they're joined together at certain points. Now when I say joined together, they're pieced together. It's not necessary that they actually join. There could be a jump, there could be a hole at those points, so we have to check. So I've got a very simple example over here. It's got two functions. The first one is x plus 3 and the second is 2 minus x. And the point we would be checking would be this point 2, where they are pieced together, because the first function ends there and the second function starts there. So the first function is ending at 2, not included, and the second function starts at 2, included. So let's look at each one of those. So the function value at 2 is 0. So it's actually going to determine that one there because 2 is defined in that one. Sorry, the function is defined there. So it's going to be 2 minus 2, which is 0. The limit when x approaches 2 from the left hand side is 5. And when x approaches 2 from the right hand side, it is 0. So those two values definitely are not the same. And because the two limits are different, it indicates that there is some kind of a jump. And when the two limit values are different, the limit as such would be undefined. So you can see that limit there is undefined. And this exemplifies a jump over here. So a jump would normally be noticed with piecewise functions, but a piecewise function could also have asymptotes, as one of my examples will illustrate that. So that's the third reason for discontinuity. So in this case, the function value is defined. The limit is defined, but the lower limit and the upper limit is not equal. So the limit won't be defined as well. So that's a typical example for the third reason for discontinuity. And this is the graph that we've got. So that's my first graph piece, and that's my second one. And you can clearly see when it gets to 2, it wants to get to that point, so that there is a jump and there is a point of discontinuity. So to summarize this, if I can draw any graph without lifting my pencil, we refer to that as a continuous function. However, if I'm drawing a graph and I have to lift my pencil, of course, when there is a hole, there is a break. So in other words, I would have lifted my pencil. But if I was drawing the graph of one of those graphs where we had a hole, you could draw it without lifting a pencil. But technically, that point does not exist. So you have to lift your pencil. So if I was drawing this graph, I have to lift my pencil. If I was drawing truncus or a hyperbola graph, I have to lift my pencil. And every time I have to lift my pencil or my pen to draw a graph that illustrates a point of discontinuity. So this is from my calculator screen. So the function value at 2 is defined. The limit at 2 is not defined, and the reason for it not being defined is because the lower limit and the upper limit are not the same. So it's failed two tests, that the limit and the function value is not the same, because the function value is defined but the limit is not defined. And of course it failed the last test, the lower limit and the upper limit are not equal. So this is an example for a straight line. Now in this case, 3x plus 2, there is no restriction on the domain, so the function is defined when x approaches 0, and that would be the function value is 2. If I find the limit for x approaching 0, it's 2. The limit from the left hand side is 2. The limit from the right hand side is 2. So what we observe over here is it's met all the three conditions. That should say condition 3 there, sorry. That should be, okay, the last one. I'll correct that later on. So if all three conditions are met, the function is continuous at x equals. So this one here is saying since all three conditions are met, so that should be condition 3, the last one. Okay, let's look at this particular example. Now this is a hyperbola. So the first thing we observe that the function value is not defined. So the domain is all real numbers except 2 over 3. So we know that the limit at 2 over 3 is not defined because it's an asymptote, because the two limits, the left hand limit and the right hand limit, are different. The left hand limit approaches negative infinity and the right hand limit approaches infinity. So the function value of 2 over 3 is not defined. So condition 1 is not met. The function value of 2 over 3 is not equal to the limit because the limit is not defined. So that condition is not met. So it has failed all three tests. Since all three conditions are not met, the function has a point of discontinuity at x equals 2 over 3. So let's look at this particular function. It's a piecewise function. It's got 1, 2, 3, 4, 5 pieces. And the first thing I can clearly see over here is if x was 2, that would become 0. And anything divided by 0 is undefined. So there's clearly a point of discontinuity at x equals 2. So check for any points of discontinuity. I straight away know there is one point of discontinuity, but I need to check the points of discontinuity at -1, because that's where this function ends and this one starts. So that's where it is pieced together. Then I need to check at 0. and then I need to check at 1. So we'll be checking at 3 other points. So as I clearly said, for first and obvious point of discontinuity is when x equals 2. So the points to check are -1, 0, and 1. So that's the domain points where the function is pieced together. So let's go and check each one of them. We'll start with -1, and when I do -1, so the function value is 0, the limit is 0, the lower limit is 0, and the upper limit is 0. All three tests pass, so the function is continuous at x equals -1. So that's a point of continuity. Let's go and check the next one. And the next point I'm checking is 0. That should be just 0. That doesn't matter. So at 0, the function value is 1. The limit is not defined. And the reason the limit is not defined because the lower limit is 1 and the upper limit is 0. So when these two are not equal, the limit is confused and it comes up with undefined. So limit not defined at x equal to 0, since the lower and the upper limits are not equal. So that's a point of discontinuity. Then we are checking the last point, 1. So the function value at 1 is 1. The limit value is 1. The lower limit is when x is approaching 1 is 1, and the upper limit when x is approaching 1 is also 1. So all three tests have been passed in this case. So the function is continuous at 1. So we have identified 2 points of discontinuity, and if I look at the graph, so obviously from there to there is a jump. So when x is 0, there is a jump, and when x is 2, there is a vertical asymptote. So those are the 2 points of discontinuity. The points of discontinuity exist when x is 0 and when x is 2. So now if you look at my calculator screen, so I'm going to start with the first point, which was -1. So if I go and put that as -1, and it says that's 0. So I'll just move more to the other side, probably just make the font a little bit smaller. Then let's go and check the limit at -1, and that's 0. And let's change the left-hand limit. So that's the left-hand limit, -1. That's 0 as well. And then let's check the limit at -1 from the right hand side, and that's 0 as well. So it's continuous. Let's go and see 0. Let's change that to 0, and it comes up as 1. Let's change that to 0, and it comes as undefined. The reason it is coming out as undefined is because there's possibly a jump. So let's go and change that to 0. So approaching 0 from the left hand side is 1, and approaching 0 from the right hand side is 0. So there is a jump over there. So I can clearly see there is a jump, and hence there is a point of discontinuity. Let's go and check 1. It should pass the test because that's where we had. So let's go and check that. 1 and 1 and 1. So that passes the test of continuity. And then of course we'll go and check for 2, although we already know there is an asymptote there. So if I check 2 undefined, if I make that 2, it will be confused because it's going to -infinity and positive infinity. So that's positive infinity, and that should have been on the negative side, yeah. And it's approaching 2 from the positive side. So we can clearly see that there is a point of discontinuity over there. So that's how we examine limits and continuity and specify whether a function is continuous or does it have any points of discontinuity. So I'll